In this particular video, we're going to be discussing the photoelectric effect, and this is the project, the topic that won Albert Einstein his Nobel Prize in 1921. So the takeaways of this presentation is to introduce the early experimentation that showed a weird interaction between incident light hitting a conductor plate and an induced electron current. And using another theory from Max Planck, which is his notion on energy quanta, Albert Einstein would take the experimental findings and Planck's notion to make a theoretical foundation of this photoelectric effect. And from this, we could also be introduced to a set of units for energy called the electron volt. So it was in 1902 that we have a Philip Lenard, and it was he who was investigating this phenomenon called the photoelectric emission. So what he was able to do, he was able to take cathode tubes, which are these glass tubes with two electrodes inside. When he fired the ultraviolet radiation onto one of these electrodes, he was able to induce an electron current. And whenever the radiation stopped, the current also stops. So clearly there is a dependency between the incident light and this induced electron current. And Lenard also said that the energy of these individual electrons in this current depends on the frequency of the incident light. But despite the fact that he was able to prove this experimentally, he did not know the actual theory behind it. He did not know what's going on in the theoretical sense. But in order to understand it in a theoretical sense, we need to look at a different topic, and that's called the black body radiation. And it was a year earlier in 1901. We have Max Planck. What he did, that he also solved the problem that classical physics had, and it was the black body radiation. Black body just means they have a perfect heat conductor that emits light energy that is proportional to its internal heat energy. And so it was classical physics that said that the emitted light is proportional to the energy that's inside the black body just by the cube of the frequency, and the frequency is that of the light. So you would expect that if you have very colorful light, you should have very hot substances. And if you look at red hot iron, then that is the whole idea of the black body radiation. But the things get a bit bumpy experimentally when we go into the ultraviolet regions, and that is the region of invisible light that does, however, correlate to very hot objects. But in the classical sense, it was thought that some color came out of it. But as we know the spectrum now, we can't see ultraviolet radiation. There's no way to make this comparison between emitted light and internal heat. And so it was Max Planck who said that the relationship between light and heat is not just a power law, it's a distribution. And so that is how you have these curves here seen in this picture. It's all made by this function here. You do not need to know what that function is, but it is what these curves are produced. This function is what is producing these curves. So behind the thermodynamics and the statistical mechanics of black body radiation, the big takeaway is that Planck's correction considered the light inside any black body, the light inside acts as if it's a gas. And gas, we think of gases as these regions of free-moving particles. So that means in this case, Max Planck would postulate that light or any form of radiation has discrete wave packets, and these wave packets are particles called quanta. And so for light radiation, for instance, for electromagnetic radiation, a light quantum, or in other words, it's a photon, would have an energy of this small epsilon to be equal to hf. And f is, of course, the frequency of the light, and h, this is Planck's constant right here. So since we can describe light as particles, we can go ahead and say that this may help us in understanding the photoelectric effect. So Albert Einstein's papers, one of his first, maybe his second, that paper did a deep dive into the theoretical foundations of the photoelectric effect, which combined Lenard's experimental findings with Planck's quanta postulate. So as we know from Lenard, the individual electron energy increases with the frequency of the light. So if we have any energy from an electron, it is proportional to the frequency of the light. And we know that the light of a photon, of a light quantum, is proportional, is based on the energy frequency, and that is the epsilon is equal to the hf. So, taking these 2 points, how can a wave kick electrons out from a metal surface? Is light really a wave? And so, because particles must interact with particles, light must have quanta inside to excite or to bump and collide with these electrons. So we go ahead and consider the situation. For light to ionize metals, the metal here has a threshold energy called the work function, and it's labeled as capital phi. If the incident light coming in and hitting the metal, if that is greater than the threshold, then you have an electron current being induced. And since light has particles, since light has quanta, it can indeed interact with the electrons in the metal. And we can say that the electric energy of an emitted electron is the difference between the light quanta energy and this threshold work function energy, and that is the threshold of the metal. But what else can we describe this kinetic energy here? Well, let's consider the conservation of energy, where the final kinetic energy is equal to the initial potential energy. And since we're looking at electrons, its specific type of potential energy is the electric potential energy inside the metal. And so that would be in terms of the electron charge times the number of volts it is pushing the electron. So therefore, we can say that EV is equal to HF minus phi. And this helped Albert Einstein win the Nobel Prize in 1921. Planck got his Nobel Prize for the quanta postulate in 1918. And even though this is the photoelectric effect, which started off with Lenard's experiment, the 1921 Nobel Prize was not shared with Lenard. Lenard had his Nobel Prize in 1905 when considering the emitted electron currents, which he called the cathode rays. And so, as we are able to understand the relationship between emitted electrons and incident light, then let us suppose that the energy from the electron and of the light are equally intense. If that's the case, then we can neglect the work function and say that EV is equal to HF. So that means for single particle energies, and particles being these small bits of matter, they have very small masses and therewith very small potential energies. And so because of this very small energy in the joule scale and very small mass in the kilogram scale, let's consider a new scale of energy and mass. And this mass unit is called the electron volt. And electron volt is, well, considering that the charge of the electron is a constant, the energy that is propelling the electron is the amount of volts that is pushing that charge. And so when we go ahead and define what a single EV is, a single electron volt, that is the number of coulombs in electron charge multiplied by a single volt. And we recognize this magnitude value as the charge of the electron. And if we go ahead and multiply volts with coulombs, that is our joule. And that's how we're able to get a single electron volt. Now, supposingly that we could take an electron, the electron that's moving, and we move alongside it so that we and the electron were moving at the same speed. We detect it as stationary. So we will see that the electron will have a rest energy. And a rest energy of a moving particle would just be the number of EV the rest mass of any particle that's moving is just the number of EV extracted by the c squared. And keeping EV over c squared as a unit on its own, numerically it is similar to this value in kilograms, and it's a very small number. So therefore, when you have very small particles with negligible masses at this rate, at this scale, if put into the EV over c squared scale, then they seem more massive than they actually are. And you can take the electron mass, for example. We know the electron mass to be this value here. Put it in terms of EV over c squared, it is practically 0.5 million EV over c squared. And 0.5 million is greater in magnitude than this 9.11 times 10 to the minus 31. So the electron volt over c squared scale, it gives this mirage that particle energies and particle masses are actually massive than what they are in the joule scale or in the kilogram scale.